And now we are moving on to 2.5, the periodic table. Here we're going to state the periodic law and explain the organization of elements in the periodic table, predict the general properties of elements based on their location within the periodic table, and identify metals, nonmetals, and metalloids by their properties and or location on the periodic table. So Dmitry Mendeleev in 1869 in Russia and Lothar Meyer in Germany 1870 independently recognized that there is a periodic relationship among the properties of the elements known at that time. So, for example, it was noted that things like lithium, sodium, potassium were shiny, conducted heat and electricity, and had similar properties. And then things like calcium, strontium, and barium, also shiny and conduct heat and electricity, but less so than lithium, sodium, and potassium. They both made these tables with the elements arranged according to increasing atomic mass. However, Mendeleev actually left blank spaces in his table to predict the existence of elements that would have properties similar to things like aluminum and silicon, but weren't known yet. So this is why Mendeleev is credited with being the father of the modern periodic table. Once things like gallium and germanium were discovered, this was huge support for his work to show that he was correct. He left those spaces on his periodic table and they ended up coming true. So this is what his table looked like. Looks a lot different from our table, right? But this is the first modern periodic table. And you can see these empty spaces that he left, and some of them where you can even see him predicting some masses and what he thinks is going to fit there. So by the 20th century, there was this relationship established between atomic numbers rather than their masses. So periodic law then states that the properties of the elements are periodic functions of their atomic numbers. Okay, so the table has then been changed from atomic mass to atomic number. So the modern periodic table arranges our elements going in order of atomic numbers, starting with 1, ending with 118. So it has different parts to it. You have periods, which are the horizontal rows, and the vertical columns, which are called groups. And I have some extra slides that I put in to talk about too with this stuff. So your book focuses on the group numbers being 1 through 18. There is a secondary way of numbering the groups that I'm also going to talk about, because I have to get myself in the habit of using their numbering, but you can use either type. The 1 through 18 is I guess the newer version. I don't like it actually, compared to what I will show you later. Periods though, no matter what, we go 1 through 7. So period 1, these go left to right. Period 1 is just hydrogen and helium. Period 2, and so on and so forth. The lanthanide and actinide series that are down here, they serve two purposes down there. Right now, as far as we're concerned, they're just there to save space. Because if you try to put them in that space, then you'd have a super long periodic table that doesn't fit on a piece of paper. So we have these different classifications. We have the metals, which are shiny, malleable, which means you can hammer them into sheets and stuff, and they're good conductors of heat and electricity. Non-metals tend to be dull and poor conductors. They're also very brittle. Metalloids can conduct heat and electricity moderately well. They have some properties of metals and some of the non-metals. Going back to this periodic table picture, you have a color code in the bottom right corner, and the metals are yellow. And what you should notice is that the majority of elements on the periodic table are metals. And the other thing to notice is solids are in black. The majority are black, and they're solids. And then non-metals are the second highest number of elements. And if you notice, some of the non-metals are solids. You see black, but the other majority of them are in this red color, which means gas. And then there's one non-metal and one metal that are blue, that are liquids. So in general, metals are pretty much all solids, except mercury, which is a liquid at room temperature. And non-metals can be solids, liquids, or gases, though the only liquid is bromine, but still. They can really be any. And then metalloids here in the middle. Okay, these are kind of in between the properties of a metal and a non-metal, but they all tend to be solids at room temperature. Now, some periodic tables, I want to go ahead and kind of add this in here, have this thick line. It's usually black or some other colors. Okay, kind of like that. And every element that touches the line except aluminum is still a metal, is a metalloid. So boron, silicon, germanium, arsenic, antimony, tellurium, and astatine, these are metalloids. Aluminum is a metal, though. That's why some books and stuff don't put that zigzag anymore. They just color in the metalloids. Nonetheless, stuff to know. So now we also have some other things. The main group elements, also called the representative elements. These are groups 1, 2, and then 13 through 18. Okay? 1, 2, and 13 through 18. So basically, the representative elements are the ones that they're sticking up. Okay? And so those are the representative. And then these guys in the center, that where you kind of have that dip, these are the transition elements or transition metals. Either name works. And these are the representative. Oh gosh, no room there. Let's try this again. Representative elements. This comes into play later on. But you should know where the representative elements are and where the transition elements or metals are. The inner transition metals are the guys at the bottom row of the periodic table, the lanthanides and the actinides. That's lanthanides, actinides. Now, we also have some names for these elements. Group 1. Okay, so the very first column on the far left are the alkali metals. Group 2 are called the alkaline earth metals. And then no names until we get to group 15, which I still to this day can't really pronounce right. I think it's panicogens. I'm going to look it up. I don't know if that P is supposed to be silent or not. And group 16, which is the chalcogens. Group 17 is the halogens. And group 18 is the noble gases, or inert gases. So the noble gases just don't react with anything. So here's just this periodic table kind of showing you, they're just showing you the different group names, showing you which ones are the main groups, which are the transition elements. Okay. So these are my extra slides. This is a different periodic table. There's one, I think it's like called periodictable.com or something. There's all kinds of different ones. But I wanted to show you this one because this shows the other group numbering scheme that is out there for periodic tables. So we've seen 1 through 18. It's just 1, 2, 3, 4, 5, 6, 7, 8, all the way to 18. The other type is the representative elements are given an A. So we're gonna ignore the transition metals at the moment. And so we have 1A, 2A, or sometimes Roman numerals is used. And then we go all the way over to 3A, 4A, 5A, 6A, 7A, and 8A. Okay. And then the transition metals are the B's. So they're labeled a little differently with how it numbers. 1B is here. This is 2B, 3, 4, 5, 6, 7B. And then it's like, I think all of these guys are considered 8B. So the transition metal numbering gets a little weird, but the main group element, the A groups, those numbers, in my opinion, are really going to help later on when we start talking about things like valence electrons and even ionic charges. So let's talk about a little bit more about these different groups. These are also some extra slides from some past books that I've used. And I even have some little videos that we're going to watch. So group 1, also known as 1A on the periodic table, the alkali metals. These are solids at room temperature. Very, very reactive. We haven't talked about electron configurations yet, but they end as something S1. They have 1 valence electron, and we're going to watch a quick video on them. Don't worry too much about the electron configurations. That's just from an old slide.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
Gotta love cesium, right? Very, very reactive. So then let's now talk about group 2 or 2A in the periodic table. So these are called the alkaline earth metals. These are also solids at room temperature. Not quite as reactive as our alkali metals, but still very reactive. And now I have a quick video comparing them to the alkali metals.
Let us compare the reactivity of the alkali metals and the alkaline earth metals. As an experiment, we will put 20 cubic centimeters of water and 70 cubic centimeters of hexane into each of 4 graduated cylinders. Next, we will add small samples of the following metals to the cylinders. 1 metal to each cylinder: sodium, potassium, magnesium and calcium. In all the cylinders, we can see the metal effervescing with the release of gas. However, the speed of reaction varies among the samples and decreases in the order potassium, sodium, calcium, magnesium.
Alright, I don't have any really videos for groups 15 and 16, but group 17 or 7A on the periodic table, these are our halogens. So let's talk about them a little bit more. They are nonmetals. Now, fluorine and chlorine are gases, bromine is a liquid, and iodine and astatine are solid at room temperature. These guys are super, super reactive. In fact, let's look at it. Most of my students like this video the best.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colourless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Even so, they're both quite volatile. You can see the coloured vapours, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2 and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of a pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all 4 of these reactions are white solids, and they're all trihalides: Al3, AlCl3, AlBr3, and AlI3. Now, aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
Alright. Pretty cool stuff. And the last one, group 18 or 8A on the periodic table, are the noble gases. So these are non-metals and gases at room temperature that really are not reactive at all. Yes, there's some exceptions and extraordinary things, but in general, they're not reactive. But neon, okay, neon lights. So let's watch a video making them, as well as hydrogen and nitrogen, light up.